totally.
Why doesn't somebody take a charge and call us?
Yeah, we are also waiting for Ashish to come.
Ashish will come,
Yeah.
but before that the hall should be full. People should be standing here. Just get everybody here. What is this? No, this is.
Yes. Yeah, we should. So actually, the online idea is to also have an archived version for us, like we usually do. That's true. That's true.
So then, I know.
Physical chemistry students are not here. I'm a student of Osha.
So what are the institutional techniques you use? Jen, you had a paper in Nature that was too long ago, but I still remember that because you were a bacha, you were growing, and you're still a bacha for me.
That's the time to produce in Nature. If you see what time there is, these are all diminishing words, right? Oh yeah, it's working.
And we want to speak. Yeah, we want to have yours. It's the same one. No, their one is identical. No, we haven't switched. You want both?
You are taking mine, please.
Yeah. No, you don't need. But you will have to use that as a.
Yes.
And that one will be a slide changer. Wait for Ashish. I saw you preparing your We are actually having this got suddenly decided after our talk. After we decided to have 1 week, 1 team CSIR.
Of EL.
That's where Ashish is.
Yeah, but the deputation thing they have to like say every penny they want to open, which is
from that
That
CSIR.
OWOT, that's the reason you saw large number of people rejected. That court decided only about tendency. Please come over this.
It's a gray area. Oh, you are on leave. I was.
Yes, we are waiting for it. And you come fruit also, right?
The whole one is different.
They are the ones who
Exactly. I'm not trying to set a mix.
You know, it's interesting. J.I. Finch was directing UK, in Seattle. So he had done his office in 57, 1957. So it was an English director for an Indian. I came in Institution of Chemistry, UK. Then they celebrated 50 years. First time there was an English president. So 50 years, I used to say a bench. 50 years after, our word has changed. And it was interesting. In the golden jubilee, they chose.
Are you talking?
Of course, when it came to yes.
Yeah, but that no one said they have.
Ajit doesn't believe in myself.
Sunak has
3 years. Pocket there. They will here in.
They have rejected.
Yeah, China also.
But I don't know how about Mr. Veera. Every time.
Sorry about the delay. We are waiting for Ashish to join. He wanted to give us welcome remarks.
So we'll welcome him when he comes. I will give the welcome.
Hello.
Yeah, Ashish.
Yeah, he's coming.
Yeah, I know this is
Silent.
Yeah, this was not planned, and he couldn't postpone that whole of
Not deputation.
It's not deputation, but it doesn't eat your ear.
It doesn't eat your
It's
ear.
like your just ear. Your ear will go. Yeah, extraordinary.
But you don't
Why you suppling people around?
Yeah.
No, because they might not, they want to write something, they have all carried something, so there are tables.
It's like you're not there. Not correct. Yes. Correct.
People are pushing.
OWOT for this, but this is a 1 week, 1 theme. So the energy is so like that every lab is now hosting one thing. And different places from CSIR.
No, so I spoke.
They are
It was that time, but I did not talk
It's
about it. I just went and spoke.
get to know what we are.
So some Vietnam or something. So they asked me, is it
How was yesterday?
yesterday I couldn't attend, but it went out quite well. The program yesterday was the main inauguration, and today the students are all there. It's we are worried that after talk how many. Because earlier the plan was only to have theory group.
no, I not applied for it.
See in general how students we did just in the morning. Yeah, I think I will try to lure them saying Ashish is
Today is
now.
all good. All ended. So it will come. Hopefully it will come.
Good. Where are you getting about this nuisance? It's a rare.
Because they are. Should be done.
Okay, and yours? No, but what do you want? 91, 99. Mine was 82. So we have a big gap of 9 years, 9 years. You were doing this calculation. Yeah, I was doing this calculation. Our age difference is like about 10 years. Could be. I'm 82 anyway. You're 70. Huh? 60. And he became Musa fellow in which year? 94. 94. You?
2001. 2001 or 2001.
Insa.
Yeah. 2001.
Those days they used to make so few. Those days they used to make very few.
Very few. In fact, when Guru Sharma was the president, in his first year he was only 12. He came for very heavy criticism. But he set standards.
Sharma was IT and AK was
Insa, yeah.
and then we are taking aeronautical scientists, they came to entered for the first time in the scientific science.
Rashtrapati Bhavan.
Yeah, so, and
See, there were good traditions.
So there were a lot of presentations open. Can I close all the others?
all of them. So, and then, though I was just taking the shower, if you had introduced into the president first, he is very generous. He was interesting. Introduced to the president. On order, and they're coming out from the other conference.
Yeah, there is the other. So Ashish is also waiting for the national anthem to be played there, and then there is some protocol. I don't know exactly what is happening there. Ashish is coming, but waiting for the national anthem to be. Should we start?
Yeah, it started.
Huh?
You can
I
start.
think we should start.
So many people here.
You will give the introduction. It's my
You can start.
You know,
Yeah, you can give. Right. Yeah.
Sarika,
I haven't. Yeah, I'll start.
I think it's a good discipline to start. You can give closing remarks rather than opening. Okay?
Welcome you all. We were waiting for Ashish to give an introduction about McBain lecture. Maybe Dr. Mashelkar can give the introduction. Okay, so Ashish will do it probably at the
When
end.
you come, I'll stop and he'll give the talk.
Yeah.
Innovation.
Yes, innovation. So I will start welcoming you all and Professor Bakshi, Dr. Mashelkar, Dr. Wadgaonkar here. So it's a pleasure to introduce today's speaker, Professor Biman Bakshi. He has been my PhD advisor, so that's the special pleasure too. It's difficult to give a very short introduction to Professor Bakshi. He is a multifaceted person, a world-renowned physical chemist, and today you will hear his talk. He has come here to present his work there. But in the afternoon, he will talk to students about something completely different, and I encourage the students to join the afternoon talk at 2:30, where he will talk about more philosophical views. He writes blogs. He has authored more than 510 papers, 4 books, and these books in different aspects of statistical mechanics are currently used by students. He's come. By faculty in India and abroad, including University of Chicago, to teach the coursework. So that's, I think, a great achievement. And he loves literature, poetry, and quite often you will find him reciting by heart from poetries and literatures while discussing science. He can draw those connections too. So currently he is holding an Indian National Science Chair, which I came to know is the first Indian National Science Chair by DST SARB, and an honorary professorship at the Solid State and Structural Chemistry Unit in Indian Institute of Science. He has done his PhD with Professor Julian Gibbs, worked with David Oxtoby, Graham Fleming, Robert Zornzig. All of them are very famous names in physical chemistry. Before returning to India in 1984 to join the Indian Institute of Science, Bangalore, he is fellow of all 3 National Academy of Sciences. He is an elected member of the Third World Academy of Science and elected.
No, the World Academy of Science, not the third. Third has gone now.
Oh,
My
okay.
mistake, not yours.
Okay, an elected foreign member of the American Academy of Arts and Sciences. In the year 2020, he received this, he was elected as a member. He has received many awards. Some of them are Bhatnagar at the age of 37. He was only 37 years old when he got the Bhatnagar. The TWAS Trieste Chemistry Prize, G.D. Birla Award, Goel Prize, and many others. He is recipient of 2021 Joel Henry Hilbert ACS National Award from the American Chemical Society in Theoretical and Experimental Chemistry of Liquids,
and also the prestigious Humboldt Science Research Award of Alexander von Humboldt Foundation 2019. Journal of Physical Chemistry brought out a fresh script in his honor in 2015, and he has also published 2 non-technical books for students, and that's the reason I'm requesting students to come back in the afternoon to listen to him. One of them is Three Donkeys in Malleshwaram, and I think he will talk about it more later. But before we invite him to speak, since Ashish has joined us, I'll request Ashish to give an introduction to the McBain lecture for which he has been invited today. So Ashish.
First of all, my apologies for holding you back. There are parallel programs going at NCL, and sometimes very passionate speakers can take very long time to end their their talks. We are here to attend the 18th John McBain, the 19th, I'm sorry, John McBain lectures today. Professor J.W. McBain was the first director of NCL, and he was here from 1949 to 1952. Before coming here, he was at Stanford. He was the emeritus professor at Stanford University. And I keep wondering always, how can someone in 1949 leave a wonderful place like Stanford and decide to spend time in a city which I'm sure many Californians will know about. Today they might, but in 1949, I imagine it was very hard to know about Pune. And particularly a place which this wonderful campus was just rock. In Marathi, this place is called Pashan. We all know Pashan, but in Marathi, the meaning of that is rock. And we have some old pictures of this place before about 1949. And the picture is taken from the hill backside. And it's literally a rock, not a single tree in this whole campus. And this campus looks so different, right? So this complete transformation of this place into this superb campus was thanks to this very distinguished gentleman. So he came from Stanford here in Pune in 1949. Before that, he was, was a colloid chemist of great repute. He obtained his undergraduate degree from the University of Toronto in 1903 and a PhD from the University of Heidelberg in 1906. After that, he became a professor of physical chemistry at the University of Bristol, where he spent quite a bit of time until 1927. And after that, he moved to Stanford, where he was the first tenure-ranked professor in the chemistry department. As I said, he was a very distinguished surface and colloid chemist. He actually, therefore, knew Sir Shantiswara Bhatnagar, who was the conceiver of CSIR. They were scientific colleagues. And of course, Sir Bhatnagar was, I would say, responsible for convincing Professor McBain to take up a position here. He introduced many fundamental concepts in thermodynamics in the physical chemistry area. We all know of the word sorption. It was thanks to James McBain that the term of sorption came into the scientific literature. He worked on many other things. He posited, for example, the existence of micelles to describe the dissolution of insoluble particles, oil molecules and so on. Published about 450 papers. He is fellow of the Royal Society, won very distinguished achievements like the Humphrey Davy Medal of the Royal Society. And here, when he came to Pune, he was instrumental in building the main building that you all see as you enter NCL. It was thanks to McBain. He designed it, he conceived it, he designed it, he supervised the construction of it. He hired the first scientist, he equipped the laboratories with all the instruments, and all of that he did in just 3 years. I don't think at all today that is possible. It takes decades to build buildings today. He managed to do it in just a very short span of 3 years. And imagine in a place where there didn't exist anything. Besides the laboratory, he also built the residential colony. He created playgrounds for our kids. He started the first school on campus. He also started a cooperative store because this place was so far away from Pune city. So there was almost nothing here. So he has made sure not only he hired good scientists, but also made sure that they could live and survive and enjoy this place. Most importantly, as you enter the main building, you will see the motto, the purpose of this laboratory enshrined in the foyer of the main building. Professor McBain was responsible for that. There was a lot of discussion. As I read the history of NCL, I understand that there was a lot of discussion between him and Sir Shantiswarup Bhatnagar as to what should be the purpose of CSIR and what should be the purpose of National Chemical Laboratory. So the articulation of that purpose in such simple words, which we stand by even today, were Professor McBain's, and he wrote them down, and those were then uttered at the inaugural function of NCL by the then Prime Minister, Jawaharlal Nehru. And to ensure that, to make them immortal, we have enshrined them in the main foyer of the laboratory. He had, as an administrator, started many things that we follow even today. You know, he used to hold what were those called famous Monday morning meetings. They are no longer Monday morning meetings, but they are happening every week, where he would invite all the support functions to understand what are the problems, administrative problems or other problems that we would solve on a daily basis, and I still continue to do that. We have weekly meetings. In the 1950s, India didn't have much of basic chemical manufacturing, so he was instrumental in starting that. He said the laboratory in this decade must focus on technologies for making basic chemicals. This is what the country needed at that time. He also started many other things, for example, creating a culture of self-help in the lab. And if you read the book of Dr. L.K. Doraiswamy, he's written a wonderful book about NCL. There are many, many interesting anecdotes that he cites in that book. I'm of course not going to read all of them here today. So I think we credit Professor McBain to what NCL is even today, and therefore in his honor we started the James McBain Memorial Lecture, and today, as I said, is the 19th lecture in that series, and we are very, very happy to have a very distinguished professor, Professor Biman Bakshi here. Sarika, you read out the introduction, so we are all very eager to listen to him. I won't stand in the way. Professor Bakshi, floor is yours.
Working? Turn it on. Okay, thank you. Yeah, I think in my pocket, yeah, I do that. Yeah, thank you very much. I know it's quite a privilege to give this lecture. Long time ago I did some work on my cells. That time I came to know of McBain's name, but I did not relate it to NCL. And I'm particularly happy that Dr. Mashalkar is here. He has been one of our heroes in the, he's not much older than me, but he was one of our heroes when we were growing up. And I joined, I used to meet him in Bangalore fairly often. Those days Bangalore was the kind of a powerhouse. So, and thanks Ashish, whom I have known for a long time, and Sharika for taking care of these things. And as I said, it's quite a privilege to give this lecture. And a lot of very distinguished people have given this lecture before me. Now what I'll try to do today is, I don't know how much I'll be able to take my voyage. But essentially some kind of lectures to I think better I go there, na? So some of these developments that have taken place, the wonderful developments have taken place when we started doing research and during our MSc days also. I remember there's a book of Finner, an organic chemist who used to follow. And then there are all these chemical reactions. And they used to they hardly have any rates of those chemical reactions. Now, of course, the talk will be much broader than, and will be quite a bit of physics and biology also in this talk. So, I'll try to. Dr. Meshelkar was telling me how convergence of parallels create new discoveries. So I'll present him one of the grandest of the convergence that you'll see. So the man's quest for time goes on for a very long time. We were always wondering about time from prehistoric days, and because of these things, and then in India, this I didn't know, that we had a interesting method to measure time called Sanatoni, which is essentially about a second, which is a wink of an eye. And that was used as a unit to measure time. And these are very famous things which actually he told in Bangalore when he came. And I was telling that in some other context, at Caltech when I was giving a lecture, there was also some kind of award lecture at Caltech I was giving. And so the man's race with the time started with Manfred Eigen and won by Amit Wade. It's very interesting. I was once in Göttingen and the office next to me was Manfred Eigen. And I worked with him and wrote a paper. Sarik also worked with him as well. So this is kind of things that happened. So when Manfred Eigen started doing his work, then we were around this time. And Porter Norris got Nobel Prize by bringing fast kind of measurements in microsecond, which 10 to the minus seconds. See, when we talk of voyage, you have thousands of books which voyage through space always means cosmology. Voyage through space always thinks big length scales, big time scales. But what we are going to take today is a more, say Einstein in his last interview said a very interesting thing in 1953. And they asked him, what do you think the new developments will take place now? He said, it will not come to outer space. One should look as to insight now into the fast processes. Ultra fast was not coined, into what is happening within biological cell and what is kind of chemical. That was his, last words and that really happened. What he predicted, that developments will take place in the micro world, both in time and length. That really happened. Huge amount of all of our material science research is essentially is a consequence of much of physical chemistry and spectroscopy is because of that. So here I chronicled what are the time scales, like when we talk of picosecond, this vibrational phase and relaxation, then photosynthesis, one huge work going on now. And we have done some work on photosynthesis, actually paper came out yesterday, but I am not going to talk on that here. Electronic coherence is a big thing. So this is what the voyage through time happened. And how did it happen? Okay. So Manfred Eigen, who shared in 1967 with Porter and Norris, he was taking an undergraduate class. And in undergraduate class, he was intrigued by the statement. His teacher said, he asked the rate. He said, too fast to measure the rate. And he was, so here is an interesting slide. So this was, I was saying, our Indian ancient clock, and there was very interesting, again one of those parallels that Dr. Meshelkar was telling me. Really I am quite intrigued by that way of looking at things. So there was Stanford was the mayor who gave the money for Stanford University, and there was one more rich businessman, and they had an wager, a bet, that during the galloping of the horse in a race, is there any instant of time, all the four legs of the horse in the air, or one was always on the ground. So there was those days, I think it was $20,000, they were filthy rich. So how could you decide? They tried going into many horse races and looked into it and couldn't figure it out. They said, okay, by naked eye you cannot do it. So they hired Meyerbeach, the master photographer, to settle the debate. And what Meyerowitz did, it gave rise to our movie theater, our ultrafast spectroscopy. The Hollywood came out of because of what he did. What Meyerowitz did was set 16 cameras at certain distances and tied them with string, such that the strings were of varying length. So when you pull the string, one after the one after another shutter will go up. So he took 16 pictures like that as the horse was galloping past. And then indeed there are 16 frames here. And DC World and all the movies, the animation you see, there are 32 frames in 1 second. It's about a matter of second. And there is one frame indeed that all the 4 legs are in the air. So one of them won the bet, I don't know who, I don't remember who. And so these are the guys who ushered in. So that was, I think, the first development, and ushered in by Porter, Manfred Eigen. Actually, I worked extensively with Graham Fleming, who was a PhD student of George Porter. Now, then that was a microsecond, and what Porter did was flash photolysis, and Manfred Eigen did temperature jump method. In physical chemistry undergraduate, those are the experiments that you read, or we used to read. I don't know whether they are taught now or not. Then came the days of laser. Amazing discoveries were made in generating ultra short laser pulses of these guys. In chemistry, nanosecond laser was used by Yanli and Hirschbach, Dudley Hirschbach, to study reactions in the gas phase, like alkyl halide. This is a very interesting, and these people are so interesting themselves, and so many different things they do. I remember in Chicago, I was worried I don't having a very few papers, and University of Chicago, James Franck Institute those days was really the very best in physical chemistry, chemical physics. JCP, Journal of Chemical Physics, used to come out of that, everything, that was really great school. But the people are very good, and their paper, when I didn't have any. So I thought of writing, so I wrote a single author paper on polymer. And then I sent to Journal of Physical Chemistry. After some time, I got the letter. The one referee said, accept it. He signed his name. Other guy said, this is a problem. Dudley Hirschbach was the editor-in-chief. Those days, they didn't get editor-in-chief. They said editor. He wrote to me, Biman, since this is your first paper, I am going to accept it. I don't know how he knew me. It was on first paper. Must have done literature. This is something so singular about these people. Okay, and of course, I think some of you at least have made a wonderful speaker. Of course, the more modern times, the laser and the gave back to the work of Amit Zuel is this book. Part of the title is taken from his book, and of course, Rudy Marcus, who is a great friend of ours and is still alive in 102 and writing papers. So, Dr. Mashelkar, you are really young. So, now, one of the things that Amit Zuel did, he's credited with the measuring of the transition state. See, chemists always use the concept transition state theory, we iterate. But then, of course, a physicist will ask, have you seen a transition state? So it was just an utopia kind of thing. So Amit Zuel set out to find the transition state and detect it, and he did detect it, a transition state. That's why he was given a Nobel Prize. And he explains here how a transition state can be defined. It's an intermediate state. So if the cat very philosophically happily is sitting there, you give it a push, the cat was not prepared it, he goes and then goes and turn around, and it always, don't do the experiment with a cat too high, but you can do the experiment on a fence, and they again land exactly like this. So initial state, final state, and what is the transition state? This is, I would say, this is for the intermediate between. So it's the transition. He detected this state for a chemical reaction which was in femtosecond lifetime. So many things happened. Many of these very fast processes could be studied for the first time. So this was the time evolution that we came from microsecond or millisecond in 1950s to now this world we are doing attosecond, 10 to the power minus 10 to the minus 18 second. Femtosecond is fairly routinely done. It's 10 to the minus 15 second. And what happened as a result, many of the questions with Manfred Eigen started, for example, isomerization reactions, that happens in sub-picosecond time scale, photosynthesis, that happens in femtosecond time scale. The most important thing on life, on the act, is the photosynthesis, okay? How the plant converts solar energy into chemical energy. And that happens in femtosecond, initial processes. So these could be studied for the first time. Now I told you the voyage through time and with the wonderful things that has happened. Now what happened to voyage through length? Here also we went from, actually let's go this way, through this, and then slowly length scale, our ability to study length scale got lower and lower, and ultimately we could study in the atoms, which is really an amazing thing in electron microscopy did. Okay, there is some issue here, but that I will come to later. So let us take the voyage through length. So this was Aristotle's universe. That's what became the biblical. So in Aristotle, if you go to Athens, go to Acropolis, and go and see the beautiful. Still there is a gallery there where Socrates, Aristotle used to all they used to. Aristotle didn't live in Athens, but Socrates was there. So this is Aristotle's universe, the Earth in the beginning. He did have some sizes right, you know, he put sun pretty big here. And we all know that this is wrong, but it took time to figure it out. It needed telescopes and all those things. So the first microscope towards was done by Zacharias Janssen, a first compound microscope. So then they slowly going, by compound microscope, they slowly go lower in time. Okay, so in between there is one slide, and so voice to continue that discovery of the microscopes, electron microscopes, and scanning probe microscopes. So all these things went us to lower and lower, almost few Armstrong time scales that people do. So we have got the time scale, which is through lasers and optical photon counting, and we have the length scale, which is through microscopy. Now these two were going parallel, okay, but still spectroscopy was not giving you length scale, and microscopy was not giving you time scale. So these two were compared in a fantastic discovery, which is single molecule spectroscopy. So here I have shown a fluorescence coming from individual molecules. When I first time saw in my good friend Paul Barber's lab, he took me when I went to Austin in 1999, he took me excitedly to Islam Biman, see the lights coming. I said, yes, so what? Well, these are coming from single molecule, MEHPPV. I said, no, cannot see a single molecule. Because I didn't quite know single molecule spectroscopy then. But he said, convinced me, yes, and showed me many. I have a little bit of result that I did with Paul in memory of him, my good friend passed away. Now here the single tetrazine molecule on a paraffin wax surface, and this one is broad because it is moving. So now you get the length scale and the time scale to combining these in single molecule spectroscopy. This is the convergence of parallel. Okay, I have talked, I am a theoretician, I have talked to you so long about mostly experiments, except I did show you one picture, it's the routine markers. Now, so the what about theory, how do you understand that what you are seeing, what you are measuring in experiment? There are two things, two pillars of theoretical science, one is quantum mechanics and another is statistical mechanics. But when you try to understand condensed matter physics and condensed matter chemistry and the phenomena in world, macroscopic world that I am standing in front of you and talking, that phenomena is through statistical mechanics. That's what Sarika does. So statistical mechanics allows the conversion of microscopic information to macroscopic observables. That is, we start with intermolecular interaction potential, which is given by quantum mechanics, and then we en route, and we develop statistical mechanics, and en route we get entropy, free energy, viscosity, specific heat rates. So everything in the world that we measure is given. So who did this statistical mechanics? You know, I must pay homage to my our heroes. All of you know Maxwell, kinetic theory of gas, but his kinetic theory of gas did not have intermolecular interactions in a way, and that was done by Ludwig Boltzmann through his H theorem and the definition of entropy. That came from Boltzmann. That's why the K is called Boltzmann constant. And Willard Gibbs, who, to read Robert Millikan, in pure science, Gibbs did for statistical mechanics and for thermodynamics what Laplace did for celestial mechanics and Maxwell did for electrodynamics. There is a beautiful sentence, namely, made his field a well-nigh finished theoretical structure. So what happened that we start in statistical intermolecular interactions, we describe microscopic states, and then we give weight to the microscopic states by entropy, and there is an elaborate formalism that takes you to, through partition function, to free energy, then entropy, specific heat, viscosity, everything that comes out from this discipline. Okay. So as I said again, the linear response functions, which are the first mentions, functions you measure. When I saw a moon first time, moon in way back in the museum in US, it was written, few things were written in the moon rocks. Its specific heat, its compressibility, and density. Important thing that students should know that these are what the most important functions are called linear response functions. They give the response of the system, and they are described by mean square fluctuations. Like specific heat mean square energy fluctuation, compressibility mean square volume fluctuation, dielectric constant mean square volume fluctuation. So similarly like that, I am not going to dynamics yet. So this is giving it a little bit of problem. Okay. I think now, okay, no, it is kind of skipping a bit. Okay, so I want to tell you two books that we have written, which Sarika mentioned. That one is the first equilibrium StatMech, which actually is doing quite well. It is being not only taught in University of Chicago, it is being used in MIT and other places. So statistical mechanics of chemistry and material science came out in 2018. That is got missing here. Now they followed up more recently. We published the non-equilibrium StatMech. So since I was talking of StatMech, this is where I discuss the postulates of statistical mechanics in, I believe, a little better way than what exists or basically after Tolman. And this is non-equilibrium StatMech, which tells you how to calculate rate, how to calculate viscosity and conductivity, things like that. Okay. After I told you about space, time, and I told you about theory. Then little bit about computer simulation. See, our theoretical calculations, everything now to a great extent is possible because of the great development of computer, which is a lot of hardware and software and all those things. And so it's, you know, it's a hugely important thing. But what in chemistry, first, so what happened when we are doing statistical mechanics, we say, okay, two particles interact with each other. And like we started from Boltzmann, two particles interact with each other and they create a configuration. Some configurations are allowed, some are not. And then we try to give weight to each configuration. So say I want to have energy. So each configuration will have an energy. Now as the configurations are changing, energy is changing. Now, so what we call, when the configuration change, we call it a trajectory. So you have this many dimensional space because you consider that you have n particle and these are atoms, 3n number of positions, 3n number of velocities or momentum. So they together describe the instantaneous state of a system. It is an extremely difficult calculation that Boltzmann tried, and Boltzmann could not do it, and Boltzmann committed suicide because he was criticized so much. Boltzmann's aim was tried again and again by other people, but nobody could really simulate an n-body particle. And you know, we are dealing in real world with the Avogadro number, 10 to the power 23. We cannot solve a 3-body problem. Forget about 10 to the power 23. Okay. many theories were developed, beautiful theories were developed by Karkut, Hausaler and other people, but still that remained. So when computer came, there was by a suggestion of John Karkut, who was again his advisor of my mentor Bob Swansea. It's very interesting. In many ways I am in the scale of 1 or 2 in our hierarchy scale. So Alder and Wainwright first did the molecular dynamics simulation of hardware system. That was with this computer that was available in Los Alamos that time. Then Anisu Rahman in Indian, he did the simulation in real liquid argon. Rahman and Stillinger did the first simulation of water. And Backhammond, they got the Nobel Prize, Backhammond got the Nobel Prize, went to biology. So because of computer, we could simulate real systems. Because of computer, we could get results. It's very important. And then computer simulation and chemistry continued with culminated in Nobel Prize in 2013. The guys who could simulate a biological reaction and enzyme catalysis and developed many different models. Okay. So now I'll talk little bit, go back little bit into chemistry. I'll come back to biology and physics later. So one is I was talking of electron transfer reaction. So this is Rudy Marcus, who got the Nobel Prize because of that. Single Nobel Prize, and is one of the most successful theory of condensed matter physics and chemistry. So what Rudy told me very interesting. He was in American Chemical Society meeting. I forgot where was that. He's a very interesting character. When he was I was in Caltech, he was teaching StatMech. At 10:30 in the night, he would send me a mail. Biman, I want to teach this tomorrow. Can you tell me which is the best book? Here is a Nobel laureate. He's 102 now. So 20 years ago, he was 82, and he was working at 10:30 in the night, preparing lecture. A Nobel laureate. So his work was a beautiful work. Before that, Libby, he said in that SAS meeting, Libby presented a work and gave this theory of electron transfer. He did it like a photochemistry. That means it goes to be excited and comes like that. Rudy said he immediately realized that this model is wrong because in order for electron transfer to take place, say let's say water molecules, cobalt 2 and cobalt 3, water dipoles has to rearrange, make it easy for the electron transfer to take place. That's the Marcus picture here. And that led to a revolution. But in the process, Marcus introduced a non-equilibrium concept of non-equilibrium solvation. That means electron is still here, it is going to go from here to there. And then what Rudy said that water molecules must rearrange properly and make it facilitate. Water molecules must facilitate. But in order to facilitate, it has to fluctuate. That means orientation should move. So the fluctuations means there are collectively a number of water molecules has to move in a direction which allows electron transfer to take place. Okay, facilitation by polarization, fluctuation of the water. Okay, but for that, how long it takes, how much it. So that was a question of that. We need to know about not how fast is solvation, and for the first time now, it was possible. This was a picture, by the way, kind of historical. This was in front of me, was drawn by Amit Zuer. Very interesting. And an experimentalist doing, look at that. We don't just an arrow. He said, no, here, this is my ground state, this is my excited state. A probe in water or any dipolar solution. The double arrow means it's getting coupled. Color means high energy. Then it starts relaxing and emitting, and see the change of the color, the red shift, we call it red shift. Energy coming down. For the first time, because of laser, one could measure this rate in water. Okay. Again, another little story. When I first time got the expression of solvation dynamics that I did not, I'm not going to show here. I took to Graham Fleming. Graham wanted that that's a very highly cited paper. Graham took out his calculator and he calculated the rate, and it came to 500 femtoseconds. Graham sadly said, I'll never be able to measure it. But in few years' time, he did measure, and this is Graham's experiment, which now came to few hundred femtosecond, actually 100 femtosecond, he could measure that. That's the way, surprising ultrafluorescent water. Water responds so fast, unthinkably fast. Water on the other hand is slow in some scale. If viscosity of water is very high, 1 centipoise, the astronaut is much faster. But at the same time, polarization, fluctuation, polarization, direction of water is hard. So, water here is an amazing liquid. I wrote a really fat book on water, and I'm writing one book more of a popular level on water, but it's amazing liquid, we all have a Bengali in word, it's simple like water, but there's nothing simple in water. So, next is, so when water was done, then first thing that comes to mind, what does water do to biology? Can we understand the role of water in biology? Because we know whole of biology, our body is 70% water, right? Surface of Earth also has 70% water. This is very interesting. There are certain amazing similarity. pH of ocean is about 7.8 or so. pH of blood is 7.4. pH of water is 7. There are certain very, very interesting things. But of course, life evolved in water. So it has to conform in ocean or way. So, okay. So when we started with a student there, we started doing something. So the question was, how fast is water at the surface of the protein? So we developed a simple theory which goes like that. It comes from these dielectric relaxation measurements of myoglobin aqueous solution. In addition to slow relaxation, which is rotation of the protein in nanosecond, ultra fast in water, about 8 picosecond, there was an in-between called delta dispersion, which was not understood. So we developed a theories. Again, these are drawn in Sarik also worked on it. Some exchange of water molecules. We say there's a dynamical exchange between fast and slow, and we said, well, two kinds of water. One is quasi-bound water and the free water, and the extra time scale that one sees delta dispersion is the transition between the two. And as well did the experiments, we seem to find the slow time scale. Okay, and that, okay. Now I want to talk a little bit, the reason I didn't spend time on that, I want to spend time on this. I told you, when I was working on mycel, I did come across the name of Bain, because he was the, as far as I understand, I might be wrong, he was the man who coined the name mycel. Okay. Okay, I told you I knew about name of Bain, but I did not know he was the founding director of NCL. It was very stupid of me because I was in the research council of NCL for several years. Long time ago, before Ashish was born. Now, though he's shaking his head. So, we did some work. That time when we did this, we said, okay, at surface of a protein there are essentially three kinds of water, mainly two. One is bound and another is free, and this bound is quasi-bound, not really bound in bound sense, that's fluctuating between free and bound state. We call it dynamic exchange model. A lot of criticism was there. First this kind of weird idea, then from India, so there are a lot of people jumped on it and said not right. So, I didn't, those days I didn't do any simulation. I was mostly pen paper theoretician. But then Michael Klein was there and he had a program, he was visiting, program of mycel. So I took help of one of his students, Bala, and then with my student and postdoc Subrata Pal, we simulated cesium pentaoctanoate, and that formed a stable mycel with 66 surfactant. And then we could get the water molecules rotation and translational diffusion coefficient. And really, it is a hydrogen bond breaking. And we indeed found that what the theory predicted. There are three kinds of water. They are tri-exponential, and these are the time constants, and this is there are two kinds of way to do the hydrogen bond breaking. Let us continue on that without getting into all these things. But there is this exact, in water, there is one which is 8 picosecond, about 5 picosecond. There one is faster than that, and there are two slower than. This is the kind of thing that Amit's well detected. Okay, and then we forward it. The following things is that there are three kinds of things, and these are their free energy landscape, more modern language. The one that is most stable is a single hydrogen bonded. 1BW, it is bound water, and is a single hydrogen bonded one is we call 1B2, and this is, no, IB1, interfacial bound water, and interfacial bound water 2, and this is, in the interface you have also free water. Okay. So different, as I said, different experimental techniques found different, and we are really heavily criticized. And we came back to that recently, and different experiments gave different things. Some experiments gave very fast, some experiments like NMR gave fast, something gave slow, and they were very confusing. What was going on? So recently we solved that, and this is a very nice poetry by Saxe, which is 6 blind men of Hindustan, which reads like this, that if you feel like, please ask questions, because otherwise it could get boring. Okay. It was 6 men of Hindustan, to learning much inclined, who went to see the elephant, though all of them were blind, that each by observation might satisfy his mind. So one guy looked at the body and said, oh, it's like a wall. One guy got the tail, he said it's like a rope. One guy got at the, and it said it's like a spear. So everyone had a different view. So these men of Hindustan disputed loud and long, each in his own opinion, exceeding stiff and strong, though each was partly in the right and all were in the wrong. This I now use to explain my, this is not working very well. Why? Okay, now, okay. The success rate is about 30% when I'm trying it. Okay. Now, this is the time. Now, look at this. What happened? Now we go, take about 6-7 proteins, look at the water surrounding the protein, and we say, okay, let, yeah, ultra fast something happened. Okay. I am not fond of this. Mine was better. I wanted to use mine, but Sarika said no. Okay. So, see, many times we look at average, and that's a huge mistake. When you calculate the rotational time or the residence of individual water molecules and made a histogram, we get a distribution. This distribution is in bulk water. Look, it is like a delta function around this 4 picosecond, delta function. But when you look at protein surface on many different proteins, this lysozyme, myoglobin protein G, and this sweet protein monilin, see how broad this distribution is. So when NMR people did, they averaged over everything and got 5 picosecond and say, well, it's just like the blind men of Hindustan. Water only is 2 times slow. Okay. Now, what I added, the time scale of Ahmed Zuhail was 160 femtoseconds. So he looked somewhere a little bit, so he came out with a longer time. Poor Konkan Bhattacharya, he had a time scale which is a 10 picosecond time resolution. So he came out with something like 500 picosecond. Each was partly right, but all of them were wrong. So this was, after we wrote this paper and we explained why there was so much controversy and fight, there was not a single paper after it. This kind of killed the field. So very interesting. You don't want that, right? You want some citations, but this paper kind of settled everything. Okay. Now I'll tell you something. So after that we realized, okay, it's okay to talk of protein hydration, protein starvation, but that's not really real biology, right? You want to know what water is doing in real sense, and that's really very, very fundamental question. What is the functional role of water? So these are the two. I have a son, young, who used to be a poet, and he has a way with words because he was a poet. Now he says many things about unfortunately for me, he is in chemistry and physical chemistry. So he tells to his elder son some things which get relayed back to me. Now he said, these are father's golden boys. They really these wonderful work, and I'll take some of them. So functional role of water in biology, a dynamic field. There are 2 physical regulators, in a gap of couple of years. They were just no referee comment, nothing almost. So basic idea what we found is that, so what we did was that we looked into energy of the protein, which is fluctuating. Okay, look at the beautiful Lehringer's, on difference between protein, beta sheet, alpha helix, and these things. Actually, Lehringer just copied completely from Linus Pauling. Now the protein is a very mobile object, we know that. So we calculated the energy of the protein and overall energy, and we calculated its interaction energy with water. Then we discovered something amazing. We found that the energy of protein is fluctuating, and that of the interaction also fluctuating, and they are anti-correlated, very strongly anti-correlated. This Pearson correlation function. And I don't have the table of anti-correlation, but it's like minus 0.9, this energy fluctuation. Look at the anti-correlation. Here is the Pearson correlation of the two energies. Now there's something more interesting what happened. Before, Cannister did energy of the protein, and he said that the energy of protein has a beautiful alpha fractional noise. This is a Fourier transform of the energy time correlation function, which has the exponent 0.97, only 1/8 noise, it is famous. Before, my friend Yao Omine did in pure water, he found like 0.7. We found amazing in protein energy, just total protein energy, you find water, this is water, and you feed protein. Okay, that's what I said, the referees didn't have any comment to say. Now I am in its mercy.
You turn this.
Oh, you are saying I have to turn that side?
Yes.
Okay. Then we said, okay, that is very nice to have discovered this energy, but what it is doing to real biological functions. So we did three things. One is the melting of beta helix, then is FeCO bond in myoglobin. Now we calculated the force on FeCO, that bond, from protein and from water. And same we did in hydrogen bonding, force on this hydrogen bond because of protein and also because of water. I'll come to the why water playing such important role in a minute. Then we found there is again this friction on them is tremendously anti-correlated, and as a result of that, you are right. See, it's good to have a smart student. Now, so water is, this is a terminology used by first or somebody, what is the lubricant of life. We indeed found that the water reduces the friction hugely. So this is the one would be coming from only protein, but this is from water, cross correlation, and when you add it up, the friction becomes much smaller. Okay, it's working now, but in a slow pace. It's dying. So functional role of water, that water as a molecular lubricant. And okay, now I come to the question: why is water so important in protein function? That question has been asked many times, but here is one of the answer. I am not saying the answer, but I think first answer is that protein's interior, again you go to Pauling, protein's interior is really very low dielectric constant. We simulate protein with a dielectric constant of between 2 and 5. Since dielectric constant is very small, polarization fluctuation here is not getting screened. You need, water dielectric constant is 80, right? Everything is very heavily screened. But when I have a polarization fluctuation here, it goes deep inside because it's electrostatic interaction, right? That goes deep inside. Because of the dielectric constant of protein is so small, it cannot screen. That's why water. So it is like this. You have a protein here, and water forms. This is the same is happening in biological cell. Then the fluctuations here will be moving the protein like this. Okay, and that plays a very important role. Okay. Sarika, your model is not working.
Okay. Now total friction gets significantly
Reduced.
and then one more thing again, Shantan did.
Did you explain the anti-correlation? The anti-correlation.
Right. Okay. It is a little deep story. So what is happening? You have to go into, say, the majority of the energy, say, with the interaction with the helices. So when this energy going up, when the polarization is coming large, then they are pushing in the energy landscape of protein into one region, and on the other time, when the polarization going in the other direction, it is going down. So it is this along the energy landscape, helices are like liquids almost. You can push them around. So some fluctuations are moving in unfavorable positions. When this energy is getting, when this electrostatic energy is more, this is becoming less accommodating, because overall there is almost an energy conservation. So, okay, we'll talk to you later. Now, I'll now talk of two things very quickly, one is on protein folding. These are kind of old work, but they are very interesting for the students to listen to. That about the how, again, these ideas from different field can come, and this particularly is important in that. So, little bit of protein folding. Those of you who don't know, protein folding is a problem of a specific predetermined contact pair formation. Okay. Again, the example I usually give, I should not really hurry too much, but I tend to hurry towards the end. Say that when I melt a sodium and again I recrystallize it, if I number each member, each sodium atom, when I recrystallize, you find it nearest neighbor least has changed. Now, if I crack here and a thing and you think it's a bomb, all of you will go out. So when you come back, all of you again sit down quickly, you will find your neighbors have changed. Okay. But protein folding is a phenomenon where it has the same contact, same neighbor. That's why protein folding is so difficult, it is entropically demanding. Protein's entire activity and magic is in the pair contact formation. Okay. So it is extremely difficult to understand protein folding problem. That's what took so long to have the protein. Okay, so the first, the breakthrough experiment, which got the Nobel Prize by Anfinsen, taking ribonucleus, and he gave the denaturant, urea and beta markerpel, and he broke. Now look, here, there are these 4 disulfide bonds, and see the disulfide bonds are quite far from, along the contour, quite far from each other. Like this one forms, it will go like that, like that. It need not have to, because there are other sulfur available for disulfide bonds. So these are very strange pair contact. But when you remove again, after you denature it, you remove the urea, it folds back, and lo and behold, exactly same contact again form, and biological activity is restored. Here biological activity is gone. So this is really amazing that it again forms the same contact, however distant and kind of unthinkable the contact is, it's still from the same contact. So then everybody asked, how does it happen? You know, this kind of problem is almost now solved, considered to be solved. Anfinsen said that because that particular state, native state, is the most stable state. But that does not quite explain it, because there could be many states. And number one, that what Levinthal said, how long does it take for a protein to fold? He said, okay, in order to know I am more stable, like for example, say somebody's salary is this much, and if he wants to know that whether his salary is more than the other, less than the other, what you need to know? You need to know the salary of other people, right? if you know he's the tallest man, then you have to know what are the height of the other guys. So in order to know something is stable, you need to know the energy of not that state, but its nearest states. Now, so the Levinthal is actually very famous, but one and a half page paper only. When I was in NIH, everybody was started talking about the product. First Stringer gave a talk, then Austin Angel gave a talk. Everybody coming and giving a talk and started with Levinthal paradox. So then I asked them, the big superstars there, I said, can you give me the paper of the Levinthal? Nobody had seen the Levinthal paper. So I went to NIH, a microfiche, and fished out the paper. It was amazing, which was just this. He said, okay, let me consider the protein as 100 amino acids. It has 3 states, so there are this many configurations. Now, even if protein samples in an enormous rate, then it will take this many years. Nevertheless, protein folds in time scale of seconds and milliseconds. How does it happen? That was the Levinthal paradox. This is a wonderful paradox, Levinthal just posed the question, you guys there, and Finson saying the most stable, even if I have to sample 1% of my configurations, which are mostly rotation, little bit of translation, but you have to fit it. Okay. So how does it happen? Actually, it's a kind of I think it's a man-made problem. It's one of the example, but it's a really. So now, this parallel thinking. When Dr. Mason was telling to me, I was really thinking of this thing. When I was in 9th grade, my father, we were pretty poor. My father was a school teacher. And he used to give us a lot of books, but most of the books were from College Street, the second-hand bookstores. So one day he said, Sunday he used to go to market. He told my mother, tell the 2 sons, 2 children to be at home today. I want to say that. So he came back from his market and then got some tea made and sat down with us and brought out 2 new books, completely new penguin books. We are impressed. They are very shiny. One is of the origin of the species and the ascent of the man. That means essentially survival of the fittest kind of thing. And he taught us for 2 days Darwin's theory of evolution. That was really amazing, Then I started reading a lot. I was 9th grade, a lot of Darwin's theory. Now, after going to NIH, after this Levinthal paradox business, I went and asked Zwanzig where to start about reading. Zwanzig was most dismissive. He said, nah, I have nothing to do with your proteins. Then I went to Bill Eaton. Bill Eaton said, Biman, for physicists like you, I would suggest What Mad Pursuit by Francis Crick. I had to absorb his satire, so I went and got the What Mad Pursuit and started reading What Mad Pursuit. In that 3rd chapter of What Mad Pursuit was a beautiful chapter, Blind Watchmaker. And that Blind Watchmaker was Richard Dawkins' name of a book. In 18th century, after Darwin's theory, in the 19th century, after Darwin's theory, there was a theologist, whole biblical people were up against Darwin, right? Man cannot come from monkey. And there's a theologist who used to give this following talk. He said, look, I'm walking in the forest, and I got a beautiful watch, and then I know somebody must have made the watch. All right. It's so beautiful, so perfect. Then look at the nature. So beautiful, the flowers and 5 petals and all this. Everything is so nice, stars. So somebody must have made it. So who made it? So implication was it was a God who made that. That's what made Richard Dawkins, one of the best theoretical biologists of our time. He has also a very good Twitter account. Richard Dawkins wrote that book, Blind Watchmaker. He said, yes, there is a watchmaker, where the watchmaker is blind force of nature. When I read that, I was used to take a bus T4 from my Rockville home to NIH because you cannot park anywhere. And I immediately realized, because of my Darwin's theory, education and research on Darwin's theory, I then constructed. I went to Attila Szabo's, once it was not there, I went to Attila Szabo's office and said, Attila, I know how to do protein folding theory. And I drew the circles. I said, okay, this big circle, essentially entropy and configuration state. Attila said, no, one is too complicated, multidimensional random walk. Data aspect, one dimension, correct and incorrect. Then once we got into the act, and we actually made a simple theory, which is the, so Richard Dawkins said the following thing. He said, let me go back to Richard Dawkins, I just jumped the a little bit, because I was more to transform myself to NIH. So Richard Dawkins said, okay, let us consider a monkey typing one line of sonnet of Hamlet. Me think it is like a whistle. So there's 28 characters, including 6 blanks, 27 possible choices. Random attained by monkey would take this much. But the monkey cannot change those letters which are correct. This I did myself, only a few thousand. I got in 2000 strokes, that one line, me thinks in the way. That's what I said. When I read Richard Dawkins these things, I immediately knew how to build a model. Okay. So, let us consider, just like Attila did, 2 states per bond connecting amino acid sequence, correct and incorrect. Now, just like Richard Dawkins, correct to incorrect has a rate k0 and incorrect to correct has a penalty and lower rate k1, and they are connected by equilibrium constant, which we know in physical chemistry. Equilibrium constant, which I know is related to free energy. Now I can do this starting from a given S, number of incorrect bonds. If I say correct 0, incorrect 1, then S is number of incorrect bonds. What is the mean first versus time? And then that has this to the power n. So it is subsequent all work of the whole our work was done by full chapter was Rupert Strayer on biochemistry. I think joined with Gaonkar as Hardy probably viewers. So modest preference, bring it from 10 to the power 30 years to 1 second. Just 2 kmt. So it is. So I got so many invitation to go group meetings, but I kind of turned them all down because I knew nothing of biology. Okay. Attila probably went and gave many talks. Okay. So then we were working one thing, which is the free energy surface is Sarika. Oh no, there is a time lag. You see. It's not happening immediately. Okay. So there is something in protein folding. This is a famous Bringetz and Molyneux model. We recently figured out how to do a rate calculation from multidimensional free energy surface in a kind of in the presence of memory. And so these are example that such a multidimensional free energy surface with a fraction of native state, and they reduce density. This is a very old paper. But you could do that, and I'm not going to go into that. I think I'll just probably end with how much time now, Sarika? Okay, voice through space and time, as I was saying that these two. So these are single molecule spectroscopy. As I was saying, we are processing from tetrazine. You can do also with pentazine. This was the Nobel Prize winning experiments, kind of things that Werner did at Stanford. And so individual, you are seeing individual molecules. This is amazing. And there are a lot of techniques that go into that. History of single molecule spectroscopy, 2 slides. Werner and Odit. The ability to analyze individual molecules still amazes even the more, I think it's still valid, more zealous practitioners of this emerging field. It was emerging then. The introduction of a novel technique generates enthusiasm among these and doubts on scale, but it's still amazing that you are seeing, because we grew up, our generation, that you cannot okay. So key to single molecule spectroscopy is that you have to get a very, very dilute solution. I used to do the calculation, and you have fantastic photon detector and collector. And that would really allow you to go, the combination of three things allow you to go to single molecule spectroscopy. And these essentially showed that you have the ensemble, very large number, and you are studying all of them and getting an average. And here you are looking single molecule. If you do the average, now just like my earlier example, average gives you totally wrong information. Because the average, if I now do a relaxation, the average, I'll get this one and I'll get a huge rate. But individuals, these are the things, the microenvironments. So this is the single molecule absorption spectrum which was there. When this was done, a lot of beautiful experiments started coming out. Okay. One of them, kinetics of protein-DNA interaction, or protein diffusion along a DNA chain. Those of you smoke, this is a very interesting thing I have been asked many times. When you smoke, your guanine go into oxoguanine, which is cancerous. However, people say, oh, you cannot smoke even a single cigarette. I was a smoker, right? And now I don't smoke, but I have some sympathy, though I should not tell people to smoke. Now, but the doctors say only one puff is bad. That's really wrong. Why their doctors are wrong? Because you have these enzymes which rectifies your mistake. So there is a HOG1 enzyme that goes and reduce the oxoguanine to guanine. So they are like our angelic guys who are saving you. Otherwise, he would not survive in this environment, pollution. In Calcutta, people living in ground floor smoke 20 cigarettes a day essentially without smoking. But they still survive very happily and eating their sweets and fish, right? So, how does it do it? How does a protein, enzymes of protein, how does it find these minute things, specific things? So this was a real question, which was then again this same Manfred Eigen made a calculation and said, okay, this is the time it should take. But Manfred Eigen's time was off by a factor of 100 or more, 1000. So it was not very clear why, what is the mechanism. These are the experiments from Sunny's lab. It is called microfluidic experiments. You stretch out a DNA and then these fluorophores, they are traveling along the elongated DNA, and these are the lights from the fluorophores. And then you can find how much it is going along the DNA. And then you can calculate the mean square displacement and you can find out what is the diffusion constant. And these are the experiments. This is the strong pH dependence and all these things, but I am not going to talk into that. So there are the following issue. When the question was brought to my attention, there are the following issue. One is it doing a random walk? That was the model of Manfred Eigen and Mirny and all the people, particularly Manfred Eigen, these things. Other possibility is that it follows a very specific path. It follows around a helix. But it moves around a helix, then there are two kinds of friction or two kinds of resistance. One is that translating, another is that it is rotating. So these two things together, okay, equation of helix, such a beautiful corpus, such an uninteresting equation. So I don't want to go into that, but I derived these things which Attila and everybody used to say at Bach equation. Rotation, and this beautiful term comes in, extra term that comes in. And when you do that, this is the which came out in, it was accepted in Nature, but by that time we published the paper in Attila Zago's face, right, me and Sunny. So they called and told, no, we are going to put it to Nature Structural Biology. So this is my equation. This is the earlier things. This is a beautiful agreement between theory and experiment. Okay. So last one, this is what and I used to have Paul Barbaras give this talk in NEHPP, what it showed single molecule spectroscopy, and something about the conformation of the single molecule spectroscopy. And this is something really very interesting which gave rise to a lot of research in subsequent days. That before that used to think that NADH-PPBA, since there is a lot of polymer goes on, the stiff conjugate polymer is a Gaussian. We showed that no, it is not Gaussian, it is essentially defect cylinder. Now it is more or less accepted. And this was the simulations we produced. This is the molten globule, this is the Gaussian coil, but when you added stiffness and attractions, you get toroid and rods, but you throw in defects because those are really defect molecules. Then you get defect coil and defect cylinder. So we did quite a bit of work on insulin dimer dissociation, and insulin is what saves you from eating sugar, and it is controlled by so insulin does not itself, but it helps in removal of blood sugar by mechanism which I am not going to go into. In your body, insulin to be active, it has to be a monomer. Insulin is a monomer. I think I gave this lecture, I think in this or somewhere some time ago. Okay. Or some other. Insulin, after a long time I am talking about insulin. However, insulin in our body is stored as a hexamer. In pancreas, insulin is stored as a hexamer. Coming out of the hexamer, it becomes a dimer. But dimer has to dissociate because biologically active is the monomer. If you have seen that it shows in glycosidase, it sits there. I forgot the name of the enzyme and how the A is open and sugar molecules are absorbed and broken down. Now, so this is the dimer, is the antiparallel conformation. So how does this dissociate takes place and what happened? We worked it out, and essentially we knew techniques, and we found the beautiful role of water. I was talking about another beautiful role of water, that this is when they are separated by 5 nanometer, but surface to surface is 3 nanometer, and there is a huge number of water molecules, and these water molecules are in a state very different. Like these water molecules are much faster. This is the bulk. They are much faster in rotation. And there is a pathway when it separates. We figured out the pathway, that it's a rugged energy landscape. And we could calculate the rate. And that rate was, that was published. Now, what I want to say, how these kind of things happens. So when we did that, from that time I wanted to do a protein dimerization. The work in MEH-PPB gave rise to a lot of work, including our one, conformation of a single polymer that I showed you. Not just a Nature paper, we had several other papers later. And now when I went to Gordon conference last time, there were 2 posters which are completely on our work. They dragged me to their poster saying that, look, we did, because of the work that I did. That was done with my student Srinivas and Shumon. Yeah. So, but here, but that was a toy model. It's very important to be able to construct toy models because many times the real molecules hide the physics. So, even in glass transition that we are talking to Lele and Anjan, it is very important to have some kind of ball bearing kind of a toy model to see what is happening. Okay. So, here there is a toy model, new toy model, which is just going to be submitted. I kept 2 polymer by carbon chains essentially apart each other, and then I studied them dimerization. Some very interesting things happen when they are very close to each other. First thing, it start folding at the side, and then conformational fluctuations, and they go like that. They get attracted to each other, and then it progresses, and ultimately it forms this dimer state. Whom, if you do the order parameter, there is no difference between these 2 spaces, they are intermingled. However, if you take them 12 sigma apart, then they again start the process. So what I am trying to say, the polymer collapse actually most of the time does not help the dimerization. So it collapses, then they drift away. We found a critical distance of between these 2, which are about I think 5 sigma or so on. Sigma is the diameter of the protein. This is a insulin hexamer. I told you it stayed in hexamer. For some reason we started working on hexamer,
And when I went to one place, and Peter Waldines, who is one of the big guys, I told Peter we should work on hexamer. He said, Biman, there's money in it. Though nothing really happened with him. So I did it with those two golden boys. So we wanted to know, when I looked at the insulin hexamer, there's a cavity. So I wanted to know why there's a cavity and what is inside cavity. There was not too much information on that. So we teamed with a very smart molecular biophysicist, Gopal, and that was his student Desmukh and his Shomok Santan. And we simulated it, and they did very detailed X-ray calculations, and then we found that it 10 water molecules, and it contained, and then we did very detailed calculation, how long the water molecule stays, what are the nature of the water molecules. 4 water molecules are different, and it's a very important problem, that your insulin is, as I told you, in pancreas, it's a hexamer. Though these are in vitro, so there is an issue there. And we did that, all the different time scales. And then what happened if you remove the water molecules? Then the insulin collapses. That's probably, for a physical chemist, that's not too surprising, but it collapses out of first time scale. The day that came out, I got many telephone calls from CNN News, and they're very much big. I just have this little bit here. So they many telephone calls, and finally put together almost one full page of CNN News, and whatever they said, most of it was wrong. Even after so many telephone calls, this science editor can be interesting. So, and this a little bit of class which we published recently, saying this beautiful bifurcation in a glass. We did for the, I believe, for the first time to put orientation. So we simulated a collection of oblet and prolate, and that formed beautiful glass, so high density, low temperature. But however, when you work the temperature, the relaxation spectrum undergoes beautiful splitting. We thought it's alpha beta bifurcation, but therefore it's made us believe it's not alpha beta bifurcation. It could be MCD bifurcation, or it better just the boson peak. We have not been able to figure it out yet. So my last thing is that I did for students. I really like this Carl Sagan thing. That one glance at a book and you hear the voice of another person, perhaps someone dead for 1,000 years. To read is to voyage through time. The Carl Sagan is beautiful. He was a great writer, right? Science writer. So these are my 3 books, and one I already shown. But more than that, I wrote this book, which then INSA published it and made it finally for success, which I'll talk about today. These things, how to perform well in academia. Ashok Singhvi of INSA Vice President then was an NPL. He edited extensively and very nicely, and that's a book. The book that came out was different. And this is the that is now, I think, finally died, but it has done a good job, no? Can you do the next one? This is a book. What happened? I write blogs, and I wrote a blog, 3 Donkeys of Malaysia, and that became very popular. These are really, see, we say such bad things about monkey, about donkey, but I pointed out how great donkeys are. So when this book was published, my students called me and told me, "Sir, are you writing about us?" And this is available in Kindle edition. And so this I really always like with the poetry, as Sarika said. So this is, I read the Bengali, you read the English, that Rabindranath's last poem. Rabindranath was a strange, and I keep writing, I write more. This was when he cannot write, he was in pain. 7 days before his death, this was written. Actually, 7th, 8th, 9 days, he wrote 3 of the beautiful poems. These are the last one. And these are the very first lines. তোমার সৃষ্টির পথ রেখেছো আঁকিনো করি বিচিত্র ছলনা জালে হে ছলনাময়ী মিথ্যা বিশ্বাসের ফাঁদ পেতেছো নিপুণ হাতে সরল জীবনে. Those who know Hindi or Sanskrit will be able to follow. এই প্রবঞ্চনা দিয়ে মহত্তরে করেছো চিহ্নিত তার তরে রাখুনি গোপন রাত্রি. He used to work all night.
তোমার জ্যোতিষ্ক তাকে যে পথ দেখায় সে তার অন্তরের পথ, সে যে চিরস্বচ্ছ। Now, then he said, the path of thy creation that are strewn with deception is a very poor translation. Laid down thy way by depth within a people. He's saying that, you know, our path to creation, which is so much in our research, you know, we have to be careful. Because there are a lot of deceptions on the way. Impact factor, citation. And so this is the end, I believe. If I can go there, can you help? Thank you very much.
Questions? You have
Nobody else. No hands.
students can ask again. You can come back again at 2:30 to ask questions.
No, but there should be questions.
Yeah, that's a different talk. That's absolutely different talk.
This will
We'll
not
talk about Dr. Machelkar there.
and students.
Yeah. Yes.
Yeah.
Not a student, but.
I have a question about, so you are talking about the molecules are like, water is the lubricant in the molecular level. So is there any example water can act as a lubricant in the macroscopic level?
All around. No, because the surfaces can go against, you know.
We slip and fall.
Yeah, but it is of course not as good as the oil. But you know, if you can have two surfaces, solid surfaces. The reason you slip and fall, yesterday I was almost falling, that is because of that.
But is it the water's property or it is coming from the surface property?
No, water doesn't stick on hydrophobic surfaces.
Yes, but no, why I'm asking, there are in the biomedical research also people are talking about water helps as a lubricant. They says that line.
Right.
But I don't
But
know.
that is a macroscopic scale and this is a microscopic scale. Yeah, what we are trying to understand that water as a facilitator, you know, so long we always thought that water is kind of a, you know, it solvates, stabilizes the protein or DNA. Recently we did a paper, it came out in Great What's special issue, which is on DNA. So DNA has to form a bubble in order to act. So micro bubble, I'm deliberately going away from the question you are asking because that to me is not too interesting. Yes, lubricant, I can sleep, on ice you can sleep because the reason in ice you sleep because it just on your pressure ice melts, and you go. So those are the very, very, very trivial examples. Because for that matter, oil is a much better lubricant than water. But water also plays its role in those kind of macroscopic things.
One question is that in the molecular level, is there this water's lubricant nature, does it have any effect on the hydrophobic effect of the molecule? Because of the hydrophobic effect, water is acting as lubricant, or water inherently has the lubricant effect?
See, in a microscopic level, it is not top down, it is bottom up. That means my logic is coming from bottom, microscopic level and going up. Now, what we have shown here, that because of the nature of protein, which all of us know that it's essentially hydrophobic interior and hydrophobic interior, but what I didn't tell and forgot to tell and I should have told, that main thing I really forgot and I'm sorry for that, that the peptide bond has a very large dipole moment, 3.40 pi. So that is the reason. So water has a place to hold on. So this peptide bond has 3.40 pi. That is inside. They are such arranged to electrostatic, that's also answers our question. So now water from outside, say water is always moving and there are called polarization fluctuations, which is the reason you have dipole moment. So that polarization fluctuations, local polarity will be felt inside. Why? Because there is no screening and there is a dipole moment there. So it's like holding the ear and move it like that. I do with somebody else's ear, but okay.
Thank you.
Yeah. You know, Biman, fantastic talk.
Thank you.
Absolutely deep scholarship, and this is exactly what our students should be listening to. You know,
science at the cutting edge. We talked about the role of water in protein folding. I'm looking at unfolding, because that is where unfolding, then aggregation, Alzheimer, Parkinson, etc. What do we understand about the initial events in misfolding? Misfolding, I mean not unfolding, misfolding. How much do we understand on those initial?
That's a wonderful question. Okay, let me give you one specific example. We studied that. There is a joint body water, a chicken fillet head piece. There is a one protein, which is a part of a much bigger protein, 36 amino acids. So when you study the folding of that in our computer, it is done experimentally. This one of the fastest folder in microsecond folds. When you try to do it computer, we used to have our homegrown force feed, which everywhere people told me why I didn't make it a package, but I never had that ear for that. But we simulated 600, almost 700 trajectories. Only 4 went to anything like a folded state. So we looked into what is happening. What happened? Initially the hydrophobic collapse takes place. Secondary structure forms. Up to that there is no mistake. Now a tertiary structure like head piece that was, there is a leucine at 35 position, that has to go inside the pocket. That pocket is by 3 phenylalanines. One is phenylalanine at position 7, another is by 11, another by 18. So this guy goes and almost forms a packet, completes the pocket. Now we did one thing, is Balaram's suggestion. He told me, Biman, you are doing useless work. I said, why? He was like that, Balaram, you know. That because you are water, we never study water, we always have something else, some salt or something. I said, so what solute should we use? You said DMSO. Then we did DMSO. DMSO is a wonderful, just water DMSO is wonderful. Dimethyl sulfoxide, but when you put that, 2 methyl groups of dimethyl sulfoxide, put HP36 in water DMSO solution, DMSO comes and interact with the hydrophobic pocket and opens it one. So then you say the unfolding. So it is like a cold denaturation. So at a molecular level, one really understands what is happening. DMSO, what we didn't expect, that effect of unpacking of 3 phenylalanines and kicking the leucine, isoleucine out. But in a more complex situation.
Yeah, unfolding is one, but misfolding.
Yeah, but that was I told you, that 700 trajectories with 700 simulation, we did only 4 kind of folded. That because along the folding pathway, the real barriers come towards the end, and they are pretty deep barriers, and they form what is called molten globule, and they are a nuisance, absolute nuisance in theoretical studies, but nature always avoids it. And with the lubricant, see, our simulations much of the time we do not have water. Water again plays a lubricant role there, which facilitates, and there are other salts that's happening. That when people do protein crystallization, they always add some salts. So a lot of these other effects, which are theoretically, I would say more or less understood, but you have to take each case and then do it, and it would be a long project. But general principles are understood.
How do you understand lubrication at a molecular level? We use viscosity even from stat mech as an average property. And
Yeah,
here
but
you
you
are
have
talking
to give me the experiment. You have to give me the experiment.
So you're talking about protein folding.
Yeah, that's a very well understood, because that's at the protein folding, or in the experiments that the 2 examples I gave. One is at the breaking of a bond or a beta sheet, and the other one is energy correlation. So there it is very easy, because there is a cross correlation between protein and water, which is anti-correlated. So when you calculate the force correlation function, that's a large and negative. And that cuts down the large resistance. See, when you try to break something within protein itself doesn't allow it. Protein resists it because protein's purpose is to hold it together. But it is the water which is moving it from outside and telling it to go. So that is the molecular level. This is completely new, even if I say that myself. Now, if I translate it to your case, then just I was talking, I have to look at the interactions. What are the interactions doing? What is surface doing? And why the lubrication is coming. That I think at the macroscopy level it should not be difficult. I don't think that there will be a fundamental issue at the macroscopic level. And I would imagine that has been worked out.
So in the microscopic level, when the water is from outside pushing the protein, it is actually making some small changes in the protein structure,
Yes,
and that's what.
and forcing it to go in a way which he doesn't want to go.
Yes.
That's
So-
why chemical reaction takes place.
Yes.
But as a result,
it is
protein's energy goes up. But
The
by
stability goes down of the.
but water protein interaction goes up because it works with these peptide bonds. And in order to enhance that interaction energy, it is penalizing the.
Yes, so it's an enthalpy.
Yeah, exactly.
It is losing one
Anti-correlation.
enthalpy and
Anti-correlation.
gaining another enthalpy. But what Avijit was mentioning is probably inside the body, different organs. Now there can be hydrophobic interactions between water and organs, and that can cause the lubrication there. So probably he's talking about internal organs and lubrication there, and there can be hydrophobicity which will play a role. That's.
Any other question from students?
Yeah.
Stand up.
Sir, my question is like water dynamics very fast. So there is interfacial and bulk dynamics. So how you decide that this is the interfacial dynamics, and because it is fast, the interfacial water can also become a bulk water. So how you determine this dynamics is coming from interfacial and this is from bulk?
Interfacial dynamics in water, as you said, is a hugely studied subject. So if you think of just pure water, like the water standing here, so the water standing in a glass, we say very tranquil, but that water is very violent actually inside. The enormous number of translation, rotation taking place is a very active. If you look at the hydrogen bond breaking that is taking it, 20-30% of the hydrogen bond breaks within 100 to 150 seconds. Now, these water molecules also coming to the surface and then going back. Now, it is staying on a surface for maybe few picoseconds, couple of picoseconds. That is now known. Actually, people are saying, okay, is the water pointing its hydroxyl group upstairs or downstairs, or is it around the flat? This question is just about settled by again some nonlinear optical technique. I don't remember whether it is H points up or OH points up. So the interfacial structure is getting done, and it is. I think there was a science paper 2-3 years back. So that is getting understood, and I think there is a computationally and technically, experimentally an issue there. But I don't think that is a very fundamental in the sense, there is no fundamental difficulty. That will be done. Now, if you now asking me at a protein surface or at a DNA surface, what is the role of water? Those water which are in minor groups or major groups of DNA, or which are just surrounding. I showed one, that dielectric constant of water as you move away from the water. If you can put that up, that would be very nice. That will be around the middle. So what we did, okay, this is a protein. We took many proteins, of course. Everywhere we are studying 5 proteins. And then we consider, in order to have certain averaging, 1 nanometer layer. And then, go back. Go back. No, it was just after water. Just one slide. There's an ice. I'm surprised people didn't ask of you because you had to go faster. Oh, yeah, that one. Yeah. So now with that kind of, I can define what is in at the contact of water surface, and then go. What we found surprising now is calculate the dielectric constant, because experimentalists can calculate dielectric constant at the surface of the protein by placing a dye there, and they have a technique called some Z score, and they find at protein surface water dielectric constant is like methanol 32, 34, something like that, which is similar to what we found. So the water molecules in the surface are different from water molecules in the bulk. They are more constrained, more structure imposed by the protein, because that's a heterogeneous environment.
So that is the first layer.
Huh?
That is the first layer of.
First layer, and what we were surprised that dynamically in many ways protein influence continues to about 40-50 angstrom. We didn't, but there was an experiment by, and there's a feature article, and they spent one full paragraph in the introduction on our work, Selinger, and he does say that it was this long range, but nobody believed him.
It's 1:30, so we should.
That's because of Lele, because Ashish came there. It was not because of me.
No, not at all. Yes, so let's thank him for this wonderful talk.
Thank you.
It was really, he started from the history and went to the very recent times. And as a token of our appreciation, I would like Ashish to present him. Bouquet should have been in the beginning, but again with Ashish.
Because of Ashish, everything is Ashish's fault. So, thank you.
Here is a painting.
Oh, this I was just amazing. I was just praising this to Dr. Mashelkar. Thank you.
And a book.
Thank you. Give it to Sarika. Give this to me. Thank you.
And before we end the program, I should definitely thank the event management team, because without their help, having two parallel programs, and it's like it has gone smoothly. So the
And
whole
force
team.
the students to come.
Except for the delay, yeah, but you're not part of the team, right? So yeah, so there are large number of people who makes this event successful. So I'm not going to name them individually. If I miss one person and name the other, there will be an issue. But thanks to all of them for making this a successful event. For students, 2:30 or maybe a little later. It's 1:30 now, so yeah. So 3 probably we will start the other talk, which will be a different flavor of him and maybe more poetry and stuff. But yes,
No, less poetry. No.
less poetry. Okay, more philosophical maybe. Yes. So we will. And
Sarika has not heard of it, so.
no, but I didn't know you're going to talk. You have a poetry at the end of your talk. I just mentioned that you do recite. So yes, and everyone else can also come in. I'm sure I'm going to come and listen to it. So all are welcome. Okay, with that, let's thank him.